Hello, everyone, and welcome back to Quantitative Reasoning M155 Mathematical Modeling. In the previous video, we calculated mean, median, and mode, which I'm sure you all remembered. So it pretty much probably served as a review. Those measurements from the previous lesson tell us about the center of the data. Today, we're going to look at something different, which is how spread out are the values. Let's begin with example number one. And again, you can refer back to those terms that were visible because I'm going to be using them throughout. So example number one, mean, range, and each deviation from the mean. Okay, so find range and the deviations. So let's consider this 2, 4, 6, and 8. Right, let's find the mean first. So the mean, remember, is 2 plus 4 plus 6 plus 8. Divided by the number 1, 2, 3, 4. Number of times or the number of data pieces. So that's going to be 20 divided by 4, which is 5. Okay, so we got the mean. The mean is 5. So I'm going to let x equal 5. Okay, so x is going to be 5, right? Now we need to find the range. So to find the range is basically the max minus the min. Okay, the max minus the min. So the range in this case would be the max number is 8, the minimum number is 2. So that would be the max is 8 minus the min, which is 2. So that would be 6. Okay, so we got our range. Now we have to calculate each deviation from the mean. So the deviation formula is this, right? Okay, the deviation formula is basically x minus x with the bar over it. Okay, so what does that mean? For 2, we have 2 minus 5. Okay, because here this is basically meaning that right there. Okay, so this is basically what I'm using. I'm using each data piece minus the mean. Okay, so the deviation formula would be the data piece minus the mean. Okay, so the data or one value minus whatever the mean is. So it'd be 2 minus 5, which equals -3. And then for 4 minus 5, that'd be -1. Then for 6 minus 5 would be 1 standard deviation above, and then 8 minus 5 would be 3. Okay, so our deviations are -3, -1, 1, and 3. Okay, so what this basically means is, this is 1 standard deviation below the mean, 3 standard deviations below the mean, 1 standard deviation above the mean, 3 standard deviations above the mean. So to find the deviation of anything, it's always calculate the mean, then subtract the mean from each data piece individually, and that'll tell you what the deviations are. Okay. Example number 2, why square the deviations? So explain why deviations sum to 0 and why squaring prevents positive and negative differences from canceling. Okay, so let's add some deviations, right? So let's add the deviations that we just dealt with. We have -3. Um, and we're gonna let's we had -3, -1, 1, and 3. Okay, so watch this. So -3 plus -1 plus plus 3. When you add those up, you get 0, right? So the negative and positive values basically cancel each other out, right? So these ones offset and those two offset. So that's a problem if we're trying to actually measure spread. So instead, we have to square the deviations, right? So squaring the deviation, we have, -3 squared, -1 squared, 1 squared, 3 squared. Squaring each deviation, right, that would give us 9, 1, 1, 9, right? So now when we calculate this, we would end up with 20 instead of 0, right? Whereas, if we did square, we'd end up with 0. So squaring these will prevent us from ending up with 0. So the square differences no longer cancel. So that's why something like variance matters. Okay. So explaining squared deviations, this matters because this avoids the negation of it. Okay. Squaring deviations matter instead of basically ordinary deviations. So you always want to square the deviations to avoid them canceling out right here. All right. All right. Try the problem at the bottom. Suppose a process has the mean of 50 and a standard deviation of 2. What we want to do is compare the values 51 and 58 in terms of typical distance from the mean. Okay. So for 51, right, 51 minus 50 is 1. So 51 is only basically 1 unit above mean, right? In standard deviation units, 1 divided by 2 would basically be 0.5, right? So essentially, 51 is basically a half of a standard deviation above the mean, right? All right. So again, in standard deviation, we would basically, in standard deviation units, we would basically say, 1 divided by 2 is equal to 0.5. So we would basically say that, 51 is a half of a unit above this in terms of standard deviation. Okay. So now think about 58, right? So 58 minus 50 is 8 units, right? So 8 units is a great deal, right? We can say 8 units divided by 2. Well, that's equal to 4. So that would be 4 standard deviations above the mean. Okay. So you see the difference? We only have 1 unit to work with. Well, if we divide it into 2 parts, we would have essentially half of a unit, right? All right. So whereas if, we have 8 units, well, we divided that by 2, we would have 4 standard deviations above the mean, right? So so 58 is 4 standard deviations above the mean, and you know, and 51 is relatively closer to the mean, while 58 is essentially further away. All right, let's go on to example number 3. Compare variations. Suppose two investments have the same average return. We have, investment A. Let's say I'm just going to label it as A, and that has a standard deviation of 3%, right? And then investment B has a standard deviation of 12%. which investment has more variability, right? Um, First of all, it would be obvious, right? Investment B, because, well, investment B is essentially you got, 12% is greater than 3%, right? So a larger standard deviation means the observations are generally spread further from the mean, right? So this would be the more the more true, right? Because a larger standard deviation means you have more of a general spread. So even if both investments, essentially have the same average return, the same median is not equivalent to like the same risk variation. So investment B essentially has substantially greater variation in its overall returns. Okay. Example number 4. Suppose two classes both have a mean exam score of 80 in this example. Compare two classes using both mean and standard deviation rather than mean alone. All right, suppose, two classes have, a mean exam score of 80, right? Right. Suppose this is true, right? If we stop there, then the classes appear identical, right? You got two classes, both have a mean score of 80. All right. If we stop there, it looks identical. But suppose you got class A, and class A is, you know, we got some data for them. The mean is 80, but let's say the standard deviation is 3. Okay. And then we have class B, and of course their mean, because the mean, this says their means are the same, right? So their means are 80, and let's say the standard deviation here is 15. Okay. Class A's scores are clustered closer to 80, right? Because if the standard deviation is just 3, think about it. Three standard deviations from 80, then that means those scores are going to be closer to here. Like, folks are going to be, one standard deviation from, it might be like just 1 unit, right? Right? 3 standard deviations from it, 80, 80, 70, 77, 83. Like the numbers are going to be so close to this. That's going to be the standard deviation. Whereas the standard deviation of this 80 is going to be, like 65. They're going to be more spread out, right? So the mean tells us where the center is. Okay. Okay. So the mean tells us the center, while the standard deviation tells us how spread out. Okay. Whereas this is going to be have a more spread out data set than this right here. Okay. So that's why we should always use both rather than just using the mean. Okay. The final one is common mistake. Variance and standard deviation use different units. Okay. Suppose we're using, so a student reports variance in the original units. Explain why variance has squared units and standard deviation restores original units. All right, so suppose we're using exam scores in something like points, right? The variations are also measured in points, but we square them, right? So the units essentially will become points squared, right? So therefore, the variance would be, and let me just put this down right here. So suppose, we say, mean exam scores, we use points, standard deviation, we also use points, right? Um, And so when we square them, essentially what happens is, uh, you know, we would get points squared, right? Because, points times points is just points squared. So, variance is basically logically equivalent to squared points. Okay, or we'll say squared units, because that's what we're the points in this case would be the units. Now, if variance is essentially, let's say, if we're essentially saying, we're going to use, you know let's just say variance is 16 points squared, right? Then the standard deviation would be, would be that variable times the square root of 16, okay? Or that variable equals to the radical 16, or essentially 4 points, okay? So again, if this is variance, right? If variance is, you know, those two data points squared, right? Then the standard deviation would be us taking the square root of that, and then that would tell us what the standard deviation is. Okay, so taking the square root returns us basically to the original units. All right, so variance tends to square units, whereas standard deviation is returns us to the original units. Okay, but just remember from this lesson, okay, because all of this is very important. But remember, range is the max minus the min. Deviation is an observation minus the mean. So in other words, uh, a data point minus the mean or minus the average in that case. Standard, let's see, variance. Variance is essentially like the average or the adjusted average of square deviations. Okay. And then the standard deviation is basically taking the square root of the variance. Okay. A larger standard deviation means, more of a spread, right? Standard deviation uses more of the spread. And let's see, a smaller standard deviation, as we saw here, means it's more clustered. A larger means the data is more spread out when you're comparing data sets. When you're comparing data sets, don't look at the mean alone. Always use, center and the spread to get a better picture of the data. Okay. And that will conclude this lesson, and I'll see you in the next one.